This is problem 14.12. It's on page 599. A 50 kilogram block initially at rest is acted upon by a force P, which varies as shown. And there's a figure off to the side there that shows the force as a function of time. Knowing that the coefficient of kinetic friction between the block and the horizontal surface is 20%, determine the velocity of the block at A, a time of 5 seconds, and B, a time of 8 seconds. So we're given figure 14.12. I'll recreate it. It looks like this. The force P in, let's see, newtons versus time in seconds. Looks like this. We've got 250 newtons initially, and at 5 seconds, the force falls off to 0 by the time it reaches 8 seconds. So it begins falling off at 5 and finally finishes falling off by the time it reaches 8 seconds. Now the other information that's given is that the kinetic friction coefficient is 20%. The mass of the block is 50 kilograms. And we want to find the velocity at t equal 5 seconds and the velocity at t equal 8 seconds. Now a lot of students look at this and they get confused because the force goes to 0 at 8 seconds and they expect then that the velocity was 0 at 8 seconds. But that's not necessarily the case. Now notice that P is not the only force acting on the block. Here's the block over here. And it's being acted on to the right by force P. But that's not the only force acting on the block. There's also, of course, weight. There's the normal force. Those aren't really interesting to us because we're interested in motion in the horizontal direction, not the vertical direction. But there's a frictional force. That friction force, we know, will be equal to the kinetic friction coefficient multiplied by the weight. Now, why is it multiplied by the weight? It's because the normal force is equal to the weight force in this particular case. Because we know the package is not accelerating in the y direction, therefore the forces, the sum of the forces on the package must be 0. So we can simply substitute the weight immediately for the normal force, and there's the magnitude of the friction force as a function of the normal force. So notice that this is an equation that relates a force in one direction to a force in another direction. Okay, so this force acts opposite of the direction of P. So when we use a momentum balance and say the mass times the initial velocity, in other words the initial momentum of the box, plus the integral from 0 to t of the force, really it's a sum of forces that act on the package over time that yield the final momentum of the package. Now, since the package begins at rest, we know the initial momentum is 0, but this sum of forces must be the force P less the friction force F. Okay, so let's break this up into two components and say that the integral from 0 to t of force P dt less the integral from 0 to t of the frictional force dt is equal to the mass times the final velocity, or in other words, the final momentum. And then finally, let's solve for the final velocity. Notice this equation will be true regardless of what point in time we apply it to. We just have to be careful to make sure and integrate the force P over time when it actually exists, and the force F over time when it actually exists. So the final velocity would be equal to the integral, or the difference in these two integrals, divided by the mass of the box. Now don't be too confused about this. The integral sign, all it does is it adds up things over time. So really all we're interested in is area beneath the curve. So for example, for part A, we're interested in this area underneath the curve. Notice that this area, which represents force over time, is really the impulse of that force. It's really this whole term. So for part A, that whole term, and of course this is part A, this is to 5 seconds from 0 seconds. That's just this area. So that's 5 times 250. So that's just 1250 Newton seconds. Okay, so that's 1250 Newton seconds worth of impulse that changes the momentum of the box. Now, we have to be careful here because the friction will also act over that time. Now, the friction is a constant. That friction is just mu k mg. It does not depend on the speed, despite what your intuition may be telling you. It doesn't. And so that this would just be mu k mg multiplied by delta t. In other words, the amount of time. Because notice the frictional force would come out, it's a constant. We just have the integration of time, which would be 5 seconds worth. So anyway, plugging in the friction coefficient mu of 20%, the mass of 50 kilograms, and then the acceleration of gravity 9.81 meters per second squared, and then also the 5 seconds worth of time, we can calculate the magnitude of the impulse from the friction force. Okay, now once you do that, you should take the result here from the impulse from the first term, put them together in this equation, divide by m. You can do that. I'll let you verify the units. Notice kilogram meter per second squared would be newtons times seconds, so we have newton seconds here. When we divide by mass in kilograms, if you realize what will happen, you'll get meters per second because the seconds cancel. And the kilograms will cancel because they're in the denominator, so we'll just have meters per second. Anyway, so plug all this in your calculator, 1250, that's this, 1250. I don't have the result for this on my sheet, but whatever it is, it goes in right here. And of course, you're going to subtract it off. And then the mass, we know that's the 50 kilograms. So plug all that in your calculator, you should get 15.19 meters per second. And that's the answer for part A. So let's jot that down over here. We need a little more space. So the final velocity, 15.19 meters per second. Okay. Now, as the force P drops off, will the package continue to increase speed, or will its speed start to drop off as well? Well, if you think about it, as long as force P is greater than the frictional force, which I apologize, I don't know that number right off, it would just be this little bit right here without the time. As long as that force P is above the frictional force, the package will continue to accelerate. So the package does not reach its maximum velocity at 5 seconds. It will reach that maximum velocity at some time later. Now, as soon as the friction force is equal to the pulling force, then the speed will start to drop off after that. So anyway, for 8 seconds, really it's all the same thing. It's just that we have more area. So if we change this to part B, then we're going to have more area. Now we have to accommodate this area as well. Now, in doing that, let's see, this would be 3 times 250, which is 750, divided by 2 since it's a triangle. So I need to take half of the base. So 750 over 2 would be 375. So basically, all I have to do for part B is add 375 Newton seconds worth of impulse. Okay, so this comes out to a total of, what would that be? It should be straightforward. 1625, if I did the math of that. So there's the new impulse of force P all the way from 0 to 8 seconds. And in order to change the second term, which is still the same, the equation is still the same, but to change the second term, all we have to do is add more time. So the frictional force will act for 8 seconds instead. Okay, so now instead of putting 1250 in here, we'll put 1625, and then whatever this comes out to with the 8 seconds in it, of course, that's what we'll put in here. Mass is still 50 kilograms, and so now the result, the final velocity, we would get, or you should get 16.804 meters per second. So it's interesting that at 8 seconds, the velocity is still higher than it was at 5 seconds, which was 15.19. So here are the two answers for part A and part B respectively.